Okay, welcome back, Chemistry 2330. This is our final section for Chapter 9, Benzene Rings. And what we're going to talk about today is the derivatives related to having a hydroxy group on the benzene ring, or they're called the phenols. So, again, going back to our common names for nomenclature, we just have our benzene, our toluene, and this one right here is our phenol. So the reason it's of interest is because number one, it's got a nice alcohol group for functionality, plus it's got that lone pair, so it activates for substitution. Okay. So if we have more than one of those OHs on the system, we have what we call different derivatives here. So with just the OH on here, we have the compound called phenol. If we have a methyl group with the OH on there, we call this methylphenol. The common name is also called metacreosol, because notice this is the 1, 2, 3, so that's the meta position, and that's metacreosol. If we have two alcohols on there, we can call that benzene diol, or the common name for it is called catechol. If we have the 1,3 derivative, that's 1,3 benzene diol or resorcinol. And if we have the 1,4 derivative, that has a common name of hydroquinone. So phenols are used a lot in different types of biological systems. For example, this derivative here is called the 2-isopropyl 5-methylphenol. So you have the 2-isopropyl, you have the 5-methyl, and you have the phenol here. This is called thymol. It's an actual flavoring in a bunch of different materials. If we convert this over to a different material, such that it has an aldehyde, this methoxy group here, and the phenol, we actually have vanillin. This is the vanilla flavored material that's found in wild orchids. There's a bunch of different other derivatives here, like for example, this is the hexyl resorcinol, this is eugenol, and this is another derivative that is found in naturally occurring plants. Okay, so why are they important? Well, phenols are more acidic than alcohols, okay? Does that make sense? So let's think about this. We have phenols right here, have these two lone pairs here, and its ability to give up that lone pair is the stability of this anion, okay? So if you think about it, that these electrons here can be stabilized over this ring, okay? In the case of alkoxy groups here, we only have the electrons on the oxygen, none of it gets distributed over anything else. So the ability for us to share some of that electron density across that ring makes them more acidic. And so our pKa actually drops closer to that of acetic acid. Remember, acetic acid, our carboxylic acid, has a pKa of 4.9 right here. And our alcohols are closer to that of water at 15.9. And water, remember, has a pKa of 15.7. Okay, so it's more acidic than water, it's more acidic than alcohol, but it's less acidic than acetic acid, a carboxylic acid. Okay, so it's right there in the middle of the two. Okay, so how can we use this to our advantage? Well, I mean, again, the reason we have this here is that double the conjugation between these electrons with the pi system allow you to stabilize that negative charge all the way around the ring and then come back out onto this oxygen charge. Therefore, less time is spent with this anion at the oxygen and more time of it is being spent running it around the ring, giving us its acidity. Okay. So, can we change the acidity of a phenol? Well, yes, we can. By increasing any type of electron withdrawing group on the ring, we can increase the acidity of our phenol. So in the case of chloride ion here, we know chloride is an inductive withdrawer and therefore can withdraw electron density away from the system, making it slightly more acidic. And nitro groups are much more electron withdrawing, and so they actually have a greater dipole on there and it can lower the acidity even more significantly. Okay. So because they are more acidic than uh, alcohols, regular alcohol, they actually can react with strong bases to form water-soluble salts, okay? So we can take phenol and react it with sodium hydroxide to create the sodium salt of it plus water right here. But notice we cannot do this with regular ethanol. Ethanol is not a strong enough acid to create this salt from that system, okay? They do not react with things like carbonate. Remember, we can use this bicarbonate to deprotonate a carboxylic acid to create the carbonic acid here to make it the weaker acid, but we cannot do that with phenol. So we do not generate this material out of the carbonate reaction. So what we can use to help us with this is we can use it to help us separate things. So here we have a secondary alcohol, and here we have a phenol. Now we know from our previous thing that the alcohol is not acidic enough to be removed with sodium hydroxide to make it the salt, but we know phenols are acidic enough to react with hydroxide to make it a water-soluble salt. So in this case, if we dissolve both of these materials up in a solution of diethyl ether, a nonpolar solvent, and then we extracted it with a little bit of sodium hydroxide, the phenol is going to go into the water layer where the alcohol will not be deprotonated by the sodium hydroxide, and as such is going to stay in the organic layer. Okay, so if you remove the ether, you would end up with the cyclohexanol in this species. Then if you took that water-based species and added acid to it to reprotonate it, you will generate your phenol. So we can use the acidity difference between alcohols and phenols to help us separate them in the laboratory. Okay. So one of the other interesting features of phenols is what we call auto-oxidation. Okay. Auto-oxidation means that it can react with air or other oxidizers with no other reagents. Okay. And so what we do, what we call this is it's typically a radical chain process. And so if we think of it, that means that phenols acts as antioxidants. Okay. Because what they'll do is they'll react with peroxides and other things to create a lower oxidation species. So, for example, if we were concerned about an allylic auto-oxidation where our allylic carbon, which is the carbon next to a double bond here, is going to react with oxygen to create a peroxide. If we created that peroxide, that would be kind of a dangerous thing for us to do. We don't really want that to happen in our system. So what we would do is we would inhibit that reaction by creating a stop share.